Welcome to the mechanical engineering design presentation of the current car from the Bern Formula student team. This is the sixth season for Bern Formula student, and the car of this season, 2019 till 2021, is named Aquila. My name is Louis Stoffer, and I am studying automotive engineering in the second year. This is my first season in Formula Student because it's a 2-year season. My main task in this season was designing brackets and weld them on the chassis. First, I will show you our wheel hub designs. Then I will talk about the steering column support stress analysis, and the last topic is the chassis design with different load cases. The front wheel hubs are simple. We use the same design as the last 2 seasons because its performance had been proven. They are made out of aluminium 7075. On the outside we have the thread and the hose for the center lock nut and its securing mechanism. In the middle, the brake disc mounting is combined with the 4 wheel studs for the rim, and inside are the 2 seats for the super precision angular contact ball bearings, which are also proven by the last 2 seasons. These bearings can be preloaded by screw in the stop ring, but this you can't see on this picture because it's hidden. The real wheel hubs are more complex because they are part of our gearbox. The outside is the same as this of the front wheel hubs. On the right side of the drawing you can see the outside with the thread for the center lock nut, which is the same as the front wheel hubs. You can also see on the section view the hose for the wheel studs. Then comes the biggest diameter with this special contour. This is for mounting our brake discs. Then comes a bigger cylindrical diameter, which is for the shaft seal, and the smaller cylindrical diameter is for the bearing. Inside the wheel hub we have a groove to secure the inspection glass. Through this inspection glass we can see our gearbox oil level. On the left side of the drawing you can see different holes. The triangle ones are just for weight reduction. The smaller ones with the thread inside are to mount the planetary carrier, and the bigger ones are to mount the bearings for the planetary gears. The part you can see on the picture is one of our 2 attachments for the Formula 7 steering rack. This steering rack can hold 1880 Newton in axial direction. So we made a stress analysis for our steering rack attachments and came to a maximum stress of 31 megapascals. This is well within the safety margin for the aluminium we used. Because this maximum stress is just 31 megapascals, we had the idea to 3D print these in plastic. It would save us 70 grams, but we hadn't enough manpower for tests with 3D printed plastic. So we decided to keep the aluminum ones to be safe. Now I came to the last topic, the chassis design. Our goals for the chassis of Aquila were that the weight of all tubes is less than 32.7 kilograms from the last season. The chassis is cheaper than last year and the production takes less time than last year. For the torsional stiffness, we wanted a value between 1000 and 3000 Newton meters per degree. The values for the torsional stiffness goal or for the different load cases we have from the books of Michael Trzesniowski. We plan to measure with strain gauges the real values to dimension the parts of the next chassis more precise. To achieve those goals, we made some changes at the chassis. The biggest change is the 50 mm lower front hub, which is not just for weight reduction, but also for a better field of vision. This change made it possible to save the 1.2 kilograms of steel tube, meaning that now the total weight of Aquila's chassis is 31.5 kilograms, just the steel tubes. The unalloyed steel tubes we used instead of chromo tubes allowed us to reduce the material costs by 300 Swiss francs while keeping a safe chassis. The main dimension for the chassis are 2.2 meters by 1 meter by 0.6 meter. To reduce the production time, we designed a plug system for easy and accurate positioning of the tubes. Then a sponsor cutted all tubes with a laser to the final shape. The laser engraved at the same time the part number on each tube. That way the tungsten inner gas welding process was easier. The chassis with all welded brackets and paint weighs now 40.0 kilograms. We considered different load cases. The first is braking. For this load case, we took a value of 1.8 Gs, and with this value, we have a maximum stress of 219 megapascals at the connection of the upper front bulkhead support to the front tube. Yes, 219 megapascal is pretty much for E235 steel, but the 219 megapascals are with a one-dimensional finite element model, and the result is element nodes not averaged. With a two- or three-dimensional finite element model, it would be less. For the cornering load case, we took a value of 1.6 Gs, and the one-dimensional stress analysis gives us a maximum value of 139 megapascals. The last load case we considered is a pothole. Therefore, we took a force of 2000 Newton upwards at the right front wheel. This gives us a displacement at the wheel with a rigid damper of 22.3 millimeters and a theoretical torsional stiffness of the chassis of 2264 Newton meters per degree. Also from the load case pothole, we calculated a maximum torque of 1060 Newton meters, which is acting of the chassis. We also measured the torsional stiffness of the chassis. We did this by fixating the rear and supporting the front in the middle. Then we applied force at one side of the front in steps to measure the displacement and calculate the torsional stiffness. The result of this experiment was 1600 Newton meters per degree. For us, the chassis is stiff enough with less than 1 degree of torsion in this extreme load case. Thank you very much for your attention. We are very proud to present our chassis or mechanical engineering design, and hopefully we see us at the event.